Hey everybody, Mrs. Bodechon here. We're going to look at AKS 2B. It says I can develop and use models to predict formulas for stable binary compounds based on balance of charges. So the very first thing on your sheet is this, and it's asking you to fill out the oxidation numbers and a lot of other information, but we need to understand what an oxidation number is first. So I'm going to show you a periodic table, and these give you the oxidation numbers, okay, at the very top. Now, not every periodic table has them, but if you understand them, you'll be able to write them in yourself, okay? Notice this first column is group 1, which means that it has one valence electron. Now, we all know every atom wants a full octet, so these atoms right here are most likely going to give that one electron away to be left with a full octet underneath. Because of that, they end up with a positive 1 charge. So giving away one negative electron leaves you with a positive 1 charge, or a cation, right? So that positive 1 charge is the oxidation number. The oxidation number is just what the atom will form into as an ion, okay? So the same thing here, group 2 is going to give 2 electrons away, forming a positive 2 charge, and so on and so forth. So if we look at like our halogens, this is group 17, so they have 7 valence. They're most likely going to accept 1, right, or take an electron, leaving them negatively 1 charged. So this is what charge they will have once they have bonded, once they have formed an ion, okay? So let's go and look at our table. We are starting with lithium. So lithium, I'm just going to flip back and forth, is in group 1. You can see that. Valence electrons, because it's in group 1, it has one valence electron, and it is going to lose 1 electron because it wants to get rid of it so that it can have the full octet underneath. Its oxidation number is +1 because if it loses 1, it's going to be left with a positive 1 charge after it's lost that 1 electron. And this is how we write our ion notation. So you're always going to write the symbol, Li for lithium, and then you are going to write the oxidation number or the charge that it's left with when it becomes an ion. It's the same thing, okay? Now notice I put 2 different ways you could write this. Both are correct. One is a little bit more correct than the other. So you can do lithium 1+. Your 1+ is going to be a superscript up top, or you can just write Li+. So just like in math, there's an understood 1 there, so you don't have to write the 1. Having a plus sign indicates that there's 1, okay? So same thing with chlorine. If you look at chlorine is right here. So we are halogen for chlorine, right? Group 17. So let's go back and fill out some of this together. So group 17, which means it does have 7 valence electrons, it wants to accept 1, so it's going to gain 1 in order to have a full octet, leaving its oxidation number as -1, because if it gains a negative, it becomes negatively 1 charged. So our ion notation is Cl -1, or 1 negative, excuse me, or just Cl negative, because there's an understood 1 there, just like in math. You don't have to write it, okay? And then you can go through the rest of these. I did them all the exact same way, but look at the ion notation, because this is what's very new to us, right? Is the symbol, so nitrogen 3-. And I know in math you write like -3. Well, in science we write 3 and then the plus or minus, okay? So just kind of get in the habit of that. So magnesium 2+. And notice they are superscripts, so they're written up at the top and after the element symbol. All right, so the next one, we're predicting ionic bonds. So it says predict the chemical formula for the following elements by creating a Lewis dot model based on balanced charges. So we're going to do 4 examples here. So we know we have to get to full octets and we have to get to balanced charges. So our first one is potassium and bromine forming a bond together. So if we look at potassium, it's right here in group 1, which means we have 1 valence electron. So we're making our 1 dot for our Lewis dot diagram, plus bromine. Bromine is right here, a halogen in group 17. So it has 7 valence electrons. As a reminder, only 2 dots go on each side of your symbol for your Lewis dot diagram. So there'll be 2 on the top, 2 on the bottom, 2 on each side. But because bromine only has 7, there's going to be one side without a dot, okay? So this is representing 1 valence electron, this is representing 7 valence electron. But we're adding them together because they're going to form a bond. When that happens, what's really taking place is this electron is going over to bromine right here, okay? And that's going to leave bromine with a full octet, as you can see, and it's going to leave potassium with its dot missing because it's now donated it right to bromine. Now, does it have electrons still? Absolutely. They're just in the inner shells, okay? Its valence shell has disappeared, leaving a new valence shell with a full octet. We don't have to draw that though, because we're just drawing the bond. So what we need to have written down is our ion numbers now, our ion notation. So K plus 1, and Br is going to be -1 because it gave and it accepted, right? So our charges are now here, and then we have to balance it. So because this is an ionic bond, we can use a swap and drop method. But truthfully, we don't even need to do that right now because we've done this with just a Lewis dot diagram, and we know we need 1 potassium for every 1 bromine. So then I'm going to write it. You always write your metal first. So potassium, so K, and then Br, you're going to write your non-metal second. And you would add a subscript on the bottom for how many of each ones you need in order to bond to have a balanced charge. Well, these balance out, +1 and -1. So we know we're good, right? We only need 1 of each in order to form that bond and make that happen. So that is that one. Let's go ahead and look at oh, well, this is calcium and iodine. It's supposed to be magnesium and iodine. Whoops. Typo, you guys. Anyway, we're going to go ahead and form magnesium, which is right here in group 2. So it will have 2 valence electrons, and that's our Lewis dot diagram for that. And we're going to bond that with iodine, and iodine is right here in group 17, which means it has 7 valence electrons. So we've gone and done our Lewis dot diagram for that, 7 dots around each one. Now, if I'm just doing this, I'm only going to draw 1, right? At least initially. But the thing is, they both need a full octet. So I need 1 for my iodine. That's great. I can give 1 of magnesium to the iodine. Now this iodine is happy and it's stable. It has a full octet, but my magnesium is not, right? It still has 1 electron. It's not stable, so it would not bond. 1 magnesium and 1 iodine would never bond together because of that. So if I'm only bonding magnesium and iodine and no other elements, what do I need to do? I need to add another iodine. So if I draw another iodine, I can then donate this electron over here for a give and a take to the second iodine. And this is a bond that would actually happen because now iodines are both full for their full octet. Magnesium has gotten rid of its 2 valence, leaving a full octet underneath. So our chemical formula would be written with our metal first, magnesium, then our nonmetal, iodine, and then how many of each one we did would be written in the subscript at the bottom. There's only 1 magnesium, so there's an understood 1 there. I don't have to write it, okay? And then iodine, I used 2 of them, so I'm going to put a 2. Let's try another one. This is aluminum bonding with oxygen. So here I'm going to do the same thing. Aluminum is right here, group 13, so 3 valence. Oxygen right here, group 16, so 6. Well, if I do that, 6 and 3 give me 9, right? So it's not going to form a good bond. Let's go ahead and add another one. If we add another one, you're going to notice that it still doesn't form a great bond. You're going to have to keep doing this until you see, hey, this is going to take 3 oxygens and 2 aluminums in order for us to be stable, happy, and have full octets. So if you look at where these arrows are going, you can see 2 of these from this aluminum is going to the first oxygen, one is going to this oxygen and one from the second aluminum is going to this oxygen, and then two of this aluminum is going to this oxygen. Now, from here, we can go ahead and we can write our chemical formula, which is found right here. So metal first, Al, and I had two of them, so write the subscript 2, and then O for oxygen, and I had 3 of them, so write 3. Now there's an easier way to figure this out rather than doing it, but you have to be able to do it in all different ways, you guys, okay? So let's go ahead and look at this. Here we have carbon forming a bond with hydrogen. If I look, hydrogen is of course in group 1, so it has 1 valence electron, and carbon is in group 14, so it has 4 valence electrons. Well, 4 plus 1 equals 5, so we're not like in a match made from heaven right here, right? We need 8. So what ends up happening, and you can see from the diagram, is I need 4 hydrogens in order to complete a full octet for carbon, okay? So this is how we draw it all separate, but when we combined it and there's actually a bond happening, you can see that this is going to be a covalent bond. They're sharing, right? We know it's a covalent bond because we have hydrogen, which is a nonmetal, and carbon, which is a nonmetal, and they end up bonding. There's going to be 2 for the hydrogen on each side, because remember, hydrogen only has 1 shell and only 2 can fit in the first shell. So hydrogen is stable and happy. It has a full outer shell, even though it's not an octet, it's a full outer shell, okay? And carbon does need a full octet. So all of a sudden now it can have a full octet based off of that, all right? And this is methane, just in case you guys didn't know. So the chemical formula is CH4 because we use 4 hydrogen and only 1 carbon. Now, next one on here, why do elements in noble gas families not tend to form the bonds with other elements? Noble gas is unreactive, you guys, or it's just not very reactive at all. And that's just because it has a full octet or a full outer shell. So here's some of the elements in the noble gas family, and you can see when we draw out the Bohr diagram, they are stable, they are happy because they have a full octet. There's no reason for them to bond with another element because they don't need to exchange or share electrons in order to be stable. They already are stable. Even helium at the very top, even though it only has 2 valence, because it only has 1 shell, it's still stable because it has a full valence shell. It doesn't need to have 8, okay? All right, guys, that was 2B. Let me know if you have any questions.